All right, Algebra 1 students, I appreciate you returning for part 2 of our second lesson. Again, our second lesson being a focus on how to compare data sets when I have two or more. The first video focused on comparing data sets in their center. So we looked at this example up above with Gallery 1 and Gallery 2 and tried to decide, do we want to use the mean or the median to compare those data sets? A quick refresher, again, we said if there is ever an outlier, we use the median, and if there are no outliers, we use the mean. Okay, again, that outlier is going to drastically bring the average way up or way down, or the mean way up or way down, so we don't want to use it then. We would use the median, and if there is no outlier, we feel very safe using the mean, which is also the average, to compare those data sets. What we're going to look at now in this video, I'm going to introduce two new things to you. The first one's going to answer this essential question here. That essential question being, should we use the IQR or standard deviation to measure our spread of the data? So this time we're focusing on the spread. So really the difference in the high point to the low point, or in essence, do we need to look all the way from the high point to the low point? So kind of diving right in here, the first thing that we have to ask ourselves is this, is do we have outliers? Okay, so when deciding if we're going to use IQR or standard deviation to measure our spread, we have to first know, are there any outliers? Do we see any outliers? Well, here's our general rule of thumb, okay, when deciding which of these two to use. We use the IQR when there are outliers, okay? So again, the IQR I have over here in this box, I'll star it, is just the third quartile minus the first quartile. So we would take quartile 3 minus quartile 1, and that gives us our IQR. Well, back over here, I'm going to read the sentence again, and then I'm going to draw an example of why this makes sense mathematically. It says we use the IQR when there are outliers. So if I want to talk about the spread of data, and I have a box plot that maybe looks something like this. Let's see. We have these points. All right, we have here our minimum, our first quartile, our median, our third quartile, and our maximum. Okay, so what I'm saying here is when there are outliers, where would an outlier be on this? Right? Outliers are data points that are far away and don't belong. And again, keeping in mind, each of these four pieces are 25%. So you have 25% here, 25% here, 25% here, and then you have 25% of the data spread out all along this whisker here, right? This point right here has to be an outlier. I haven't mathematically checked yet, but just by the naked eye looking here, this doesn't belong. It's so far away from the other 75% of the data, we have an outlier. So if I'm studying the spread of this, and again, there's no story that goes with this box plot that I drew here. We don't know what this is talking about. But we're going to say that that's an outlier. And if I'm talking about the spread of data, how spread apart is the data? Again, sometimes we don't like to use that outlier in it because it's a point that's so not common and really doesn't belong, that if I use, and I'm going to introduce what's next to you is the standard deviation. If I use that, then we have to include this point. But if I'm going to use the interquartile range, I'm just talking about this middle 50%, right? And is that outlier that's over here in that middle 50%? No, right? That's part of a different 25%. If I'm looking at the spread of the data and I look just at the middle 50%, that's really like my like the more average data points in all 100% of this data. It's not the it's not the high extremes, it's not the low extremes. It's kind of smacked up there in the middle. Those are the 50% that seems the most representative of this data. You have your two middle 25% making up that middle 50%. So if we're ever asked to measure the spread of data and we know that there are outliers, we want to use the IQR. The IQR focuses on that middle 50% and it ignores outliers, okay? So jumping down below here, okay, we want to use standard deviation when there are not outliers. So if we get no outliers, we know there's none. We're looking at a data display, a graph, and we can tell that there's no outliers. It's very obvious. Or if we get a set of numbers and we mathematically check, are there any outliers? We're gonna focus more on the standard deviation. And standard deviation doesn't mean much to you right now because this is the first time you're hearing it, seeing it. So I want to take a second to kind of walk you through what standard deviation is. I want you to focus on this as well. Don't focus on the math, okay? On memorizing how to do the math from start to finish. That's not the goal. The goal is just to really get a general idea of the concept, right? What does standard deviation look like to our eyes? What's the formula? And then kind of what are some things that we can do with standard deviation? Okay, so I'm going to start with something that looks kind of like a heap of a mess here, and that's this box. This is the actual formula for standard deviation broken down. And as you can tell right now, there is a lot going on right there. So it tells us what every single one of these pieces are. S right here, it says S equals, which S is our standard deviation of the sample. So our standard deviation is, we have here this Greek symbol, which stands for the sum of. So we're taking the sum is addition of this large group of things, right? Well, what is this group of things? X right here is each value in the data set. So say that we have 15 people in our data set. That's the value of all 15 minus, okay, this here is the mean of all the values of the data set. So if we went through that data set and found the mean, which we know how to do, okay, it's just displayed here as this X, and then we have that squared to the power of 2, so we square that, and then divided by n. Well, n is the number of values in that data set, okay? And then at the very end, we square root that answer. That's what that square root symbol is doing right there. A huge mess. And again, I'm going to repoint to this. I'm not asking you to memorize that formula. I never will in this course, okay? I just generally wanted to show you because I think it's doing you justice and it's me giving you an opportunity to see it. That's what's happening when a standard deviation is being calculated. Now, that thing together looks pretty messy, but separately, those things, I think, are all things we could answer. Can we find the sum of something? Yeah, we can certainly add here in Algebra 1. Can we find all the data points? Yeah, they're always given to us, right? Whether it's by numbers or by graphs. Can we find the mean of all those? Absolutely. Can we square numbers? Absolutely, right? Times it by itself. Can we divide? Yes. Can we square root? Yes. Just a long process. Well, what does that do for us visually, right? When I do all that, what is that telling us? Well, we would see a certain graph that looks maybe something like this, right? And we see these standard deviations. This right here would be our median, right here smack dab in the middle. And then you see 3 numbers to the right and 3 negative numbers to the left. When you have your first standard deviation, if I would say look at the first standard deviation, that covers from 1 to -1. And we see here it covers 68% of the data. Okay, so I might say something like what I could ask you, 68% of the data is how many standard deviations away from the median? And you would just say it's 1, right? And as I get farther away, I'm going to see if I can switch colors here. Let's go ahead and go with an orange. As I get 2 standard deviations away from the median or from the middle of the data, I now cover 95% of the data, right? Look, that makes more sense. It's not just covering up this middle part of the data. It's covering up the middle part and these 2 sections here, right? That's covering 95% of our data, right? So the large majority of our data is within 2 standard deviations. And then if I asked you what percent is 3 standard deviations away, you would go all the way out here to 3 standard deviations away. And we see that is 99.7% of the data, which includes these 2 pieces on top of those orange sections of the data. 99.7% of the data is within 3 standard deviations of the spread. And you can tell this thing is pretty symmetric, right? We're going to focus on that in the next lesson, but lots and lots of the data is in the middle, and it starts to evenly spread out towards the right and the left. You don't have something that's looking like this, where it kind of just tails off over a long period of time. Very symmetric. That's why we talked about no outliers, right? When there's no outliers, we want to use the standard deviation. This is something that has outliers. Not a pretty drawing, but these things, these data points over here are far away from our median maybe, or our mean, right? So we would not want to use standard deviation for that. Again, I have a drawing just down here below this chart. Very good to use when you get this kind of mound shape that's symmetric or even on the left and the right, okay? So that's something we want to focus on, standard deviation there. I want to take a moment to walk you through really some standard deviation examples where the math, you can follow along the math with me so you get a good idea of really behind the scenes what's being done and then what that can do for us, standard deviation, what kind of questions that can answer. So I'm going to bring us over to this slide and hop right in. I want to hop into a real life problem where standard deviation and measuring the spread is going to help us out. I have here in this problem, it says the table shows the number of cars sold by an auto sales associate over an 8-week period. It says how much variability does the data show? So variability, the more variability you have, the less predictable you have, or excuse me, the less predictability you have, right? It's saying if this data is really spread out, we don't know. This is his last 8 weeks of selling cars. If we think, or if we determine that data is really spread out, his 9th week, we might say it's not very predictable. I don't really know how many cars he's going to sell because his cars are kind of all over the place. Where if the variability is small, right? If the variability is small, then we're saying that, hey, we can probably predict that, right? His number of car sales does not vary much. So his 9th week of sales, we can probably guess and be confident that we know how many cars he's going to sell. But there's math to be done to figure that out. What we're going to do is I want to walk through this example here. So it says, again, you can find this variability by using the formula for standard deviation. So there we have this formula for standard deviation that I showed you on the last page. It is a big mess, right? You have everything that I showed you. We're going to walk through this step by step, okay? So here's step number 1. It says find the mean of the data by finding the sum of all the data points. So again, we've done it before. Take all of these, add them up, divide by 8. When we do that, we get 17. So on any given week, he's averaging, or his mean is 17 cars sold per week. We see a 17 in there, right? And he certainly has a couple weeks below that, and he certainly has a couple weeks above that. And that mean right there we found, or that was found for us, is 17. Okay, on to the next step. So now it's having us do, let's see if I can move some of these. It's going to have us check out each of these points. So it's really copied these points from up above, all 8 values, and it's placed them, let's see right here. It's placed them right here, right? Okay. So then this whole entire list is 17 because we use the mean in every single one. Again, that formula is the square root. I'm going to have it over here of standard deviation is the square root of the sum of every single data point, which is here, those list of x's, minus the mean of the sums squared divided by and minus 1. Okay, the number of data points minus 1. Okay, so we have this here. And then this math that's being done, pretty simple. It's being done vertically. 18 minus 17 is 1. Okay, then 1 squared is 1 because 1 times 1 is 1. 25 minus 17 is 8. 8 squared is 64. Here's again, 18 minus 17 is 1. 1 squared is 1. 10 minus 17 is negative 7. Negative 7 squared is 49 because negative 7 times negative 7, a negative times negative is a positive, right? We're going to keep going. 17 minus 17 is 0. 0 squared is 0. 15 minus 17 is negative 2. Negative 2 squared is 4. 18 minus 17 is 1. 1 squared is 1. And 15 minus 17 is negative 2. Negative 2 squared is 4. So it's taken all of those 8 data points, found out how far they were from the mean itself, which was 17, that whole row of 17s we used 8 times, and then it squared those, right? It squared that value. Step 3, moving along. It says the variance of the total population. So how much do things vary? Again, that's a word I just used a little bit ago. Often is noted as S squared, is the mean of the squares of the difference between each data value and the mean. So again, we're just saying, hey, we need to, at the end, we need to square root this to get S by itself, right? We always do the inverse. So the inverse of squaring is square rooting. Keep that in mind. We're taking all 8 of these mathematical values that we found there in red, and we're adding them because it's, again, the sum of And when we add them together and divide by 7, we get 17.71. And the last thing to do is to square root that. So we find the square root of 17.71, and we get this number here, 4.20883. Since this is cars being sold, we can't have decimals because you can't sell 4.2 of a car. You just have this, we round it, it rounds down to 4. So the standard deviation, right, of his cars being sold is 4. Okay, something to keep in mind. Now, what can we do with that? We have a conclusion here. Sorry, that's my dog barking in the background there. What's our conclusion? Okay, our conclusion is this. It says the standard deviation of cars is about 4. Okay, we found that. It was kind of done for us. We got to follow along. And the mean is about 17. So again, on average, he's selling 17. His mean is 17. Well, what can that standard deviation of 4 do for us? Okay, that means if I add 4 to 17 and I subtract 4 to 17, so I'm going to, again, 17 minus 4. What am I getting? So 17 plus 4 is 21, and 17 minus 4 is 13. Okay, so keep those numbers in mind. It's saying about 68% of the time, he's selling somewhere between 21 and 13 cars. Where does that 68 come from again, right? Well, that 68 comes from this number right here again, right? That first standard deviation, okay? 68% of the time, he, in this example, is selling between 21 and 13 cars. We added 1 standard deviation. We went up 1, right? And we went down 1. So we can say, hey, on a large chunk of the time, 68% of the time, is not some bulletproof guarantee, right? 68% of the time covers, roughly between 3/5 and 4/5 of the time. But there's going to be times, that means roughly 32% of the time, he's going to sell more than 21 or less than 13 on average, right? There were no outliers, so we're very, very safe saying, hey, his standard deviation is telling us that he's going to sell somewhere between here on any given week, right? We can kind of make that prediction. That can help him when he pays his bills. Hey, I need to sell so many cars. I need to sell so many cars when I have bills to pay, right? I have to plan for my family. I have to financially plan. We can use standard deviation to help him find that prediction and use that in the future. So something I want to do here next is I want to take a dive into a second example here, okay? So we have this example, standard deviation again. What does it look like? What can it tell us? What kind of questions can we answer with it? Again, assuming that there's no major outliers. So it says here in the second example, the table displays the number of points scored by a football team during each of their regular season games. It looks like we get 2, 4, 6, 8, 10, 12 regular season games. It says what are the mean and standard deviation for this data set? Well, the mean, okay, add them all up, divide by 12. When we do that, it looks like, I'm dividing by 16. Find the mean of the data, divide by 16, 2, 4, 6, 8, 10, 12. I don't think that number should say 16. I think that that's a typo. I think that should say 12. It says next here. Let's go ahead and check it. When we do that, we get 16.8. Okay, now we have the standard deviation. Tons and tons and tons of math being done for us. I'm going to show you where one of these numbers comes from. Okay, we're taking this 51.38, and then the rest of it over here kind of will explain itself, is coming from, it looks like 16.8 minus 24, which would be roughly, it should be like 7.2, and 7.2, negative 7.2 squared is going to be, well, 7 squared is 49, so 7.2 squared is going to be a little bit more than that. It's 51.36. Again, it's finding the difference of our data point and the mean, and then squaring it. We get this 51.36, and then it did it for all 11 other data values, this arrow right here. And then we find the sum, so it adds them all. We divide by 12 because there's 12 data points. We get this here. And again, we need to get this sum by itself. We have the sum squared equals 53.8. Well, we got to do the inverse of squaring, square root both sides. gone. We get the sum is. It's probably going to tell us here. What do we got? The standard deviation. Okay, we take the square root. Whoops. Can I get rid of this? No, eraser. I want to get rid of this. And I'm going to find out that can we get there? The standard deviation is 7.3. Again, this is talking about points of a football game. So can we have 7.3 points in a football game? It's probably going to have us round down. So let's call it 7. The standard deviation is 7. And we know that on average up here, it's saying 17 points are being scored on average per game. If our standard deviation is 7, well, what's 7 above 17? And what's 7 below 17? Well, 17 plus 7 is 24. 17 minus 7 is 10. So it's saying on 68% of the games, they're going to score somewhere in between 24 and 10 points. And I think that's what it's going to tell us here if I move these couple of things and let us check it out. It says the mean number of points that the team has scored is about 17. Yep. The standard deviation is about 7.3. This means the team scored between 10 and 25 points per game, 68% of their games. So a large portion of their games, within one standard deviation, they're scoring somewhere between 24 and 10. If we wanted to guess that a little bit further, we could use standard deviation further there, but that's as far as I want to go on that question there. So let's take a look at a third example of standard deviation with a lot of the math being done for us. We have this additional example 3. Additional example number 3. And we're going to go ahead and look at it. Has, based on the line plot, what data values are within one standard deviation of the mean. Calculate the mean and standard deviation first. Let's see if it can do it for us. The mean here, 5.3. Standard deviation, 1.68. It says the data values within one standard deviation are, so again, 3.62 to 6.98. So let's see, where did those numbers come from? 5.3 plus 1.68 gives us roughly 6.98. And then we take again that mean 5.38 minus 1.68, and we're given there 3.62. So where is above this number and where is below this number on our dot plot up above, right? They chose to use X's instead of dots. Well, above 3.68 we have here, and below 6.78 we have just right here. So this is our first standard deviation. These are the points that are included in that 68% of the data. I do that so weird when I know I'm writing an 8 and then a percent sign. 68% of the data falls right there. It's looking like our second deviation would probably include these values here, and then our third deviation would include these values here, giving us that general symmetric shape because there's no outliers, right? So we're going to use that standard deviation. Okay, so that can be answered much quicker there, especially when that math and those numbers are given to us. Let's take a look. We've got another example or two I'd like to check out. I think we have this one here. It says this histogram shows the lifespan sample of light bulbs from 2 companies. So we have company, it looks like brand A, brand B. It says the first shows a sample from brand A and the second from brand B. The red lines indicate the mean and each standard deviation from the mean. So we have the mean is just this bad boy right here, there, and there. And then it looks like it's showing us the first standard deviation, the second standard deviation, and the same thing up above. First standard deviation, second standard deviation there. Solution, well, what's it asking us? Compare the distribution lifespans for the 2 light bulbs. It says both brands of light bulbs have an average life of 1,200 hours. So we see that again. We see that here. We see that here. Roughly, the standard deviation for data set brand A is less than the standard deviation for B. So it looks like these things are closer together here. Right? They're a little bit more spread apart here. It suggests that brand A has less variability for their lifespan, right? So when you're buying one from brand A, you generally know what you're getting more than when you buy one from brand B. These are less predictable. They're covering a larger span of numbers. It has a bigger standard deviation, so it has more variability and less predictability. I'm not a great speller. I'm not confident in my word predictability right there. So again, the more spread out it is, it has more variability, and it has less predictability. If we buy a light bulb from this company, we have a less chance of knowing how long it's going to last than if we buy it from this company. We get a lot of our data in here in the middle, right? So this one here has less variability, and it has more predictability. Okay. Still not thinking that's right. Don't judge my spelling there. So just a general, again, data is more packed together. It has less variability. The data varies less, but it has more predictability. We have a good idea of where the next one's going to fall. Okay. So again, I want to go back to, I want to go back to looking at our notes from earlier. Okay. And what I want to do is just kind of summarize that. So we want to, when we're looking at a data set, try to find out if it has what its standard deviation is. Sometimes we have to find it. Okay. That's all that math I told you don't necessarily worry about. That's going to be pretty rare, but we want to study it and understand it. So the more close data is when we get one of these versus one of these, I'll do this example here, or even a box plot that looks like this. Right? These two right here have an outlier. Outliers are over here dragging this data over towards the left. Outliers over here bringing the data to the left. These have less predictability, and they have more variability, right? Those data points vary. We get some extra low points in these two, where this one right here that's very uniform, very symmetric, has less variability, and it has more predictability. Okay. I had something in my head that just slipped me. Just know that the larger your standard deviation, you have more variability and less predictability. Okay, because those things are being spread out. So the bigger a standard deviation, the more spread out your data is. So you can generally just look at any of these graphs and say it's spread out. We're going to have a bigger standard deviation. We're going to have more variability, and we're going to have less predictability. Versus you can see data that's real tight and packed together, maybe even something like this, lots of data points in here. We can say, hey, it has a smaller standard deviation, it has less variability, and it has more predictability. Okay, just some things to keep in mind there. We already got a chance to look at that example. So I appreciate you following along. That is all for today's lesson, and we are going to give you a chance to practice these skills. Thank you for following this second video. Talk soon.